So good, maybe morning, afternoon, evening to everybody. I'm very happy to welcome you and welcome Conrad Wasko, our speaker today. This is the first webinar organized inside the working group Hydrologic Design and Communication, particularly more interesting for the subgroup on floods that is co-led by myself, Abinesh and Yu Yang, but of course I think it's of interest for the whole working group. So I'm very happy to welcome Conrad. Conrad is from the University of Sydney, and today's talk is about rainfall, climate change, and how to update flood guidance, in particular the work that he did on flood guidance in Australia. So Conrad, the floor is yours. I give you condivision of the screen.
Yep.
Just a second. Okay. Now you are allowed to share the screen.
Good. Oh, excuse me. There we go.
Okay.
How's that?
Perfect.
Excellent. Thank you for the introduction. I will take just a brief moment to introduce myself if you haven't met me before. So I started my working career after graduation actually as an engineer at a hydraulics laboratory, and it was a consulting laboratory. So this is an example of some work that we were commissioned to do to actually build a physical model of a floodplain and to model the flow around the buildings. And so that consulting work, I guess, gives the flavor of the research that I've ended up doing. A lot of it applies to design flood estimation. I think many of you know Professor Ashish Sharma at UNSW, so it's worth noting that my PhD was done with Professor Ashish, looking at extreme rainfall statistics and how they relate to temperature. And then I was quite fortunate that I had 2 research fellowships back to back at the University of Melbourne, working a lot with Rory Nathan, who is one of the leading consulting engineers in Australia, who then transitioned to academia. And I think people often say, because it's getting close to 10 years since my PhD, and I say, oh, I'm teaching for the first time, and they're like, how did you avoid teaching for 10 years? But I did, but now I am embarking on, I guess, what you call a tenure track position at the University of Sydney. So I have teaching and research. And the photos there are just 2 small tidbits. This photo I like because these were 2 PhD students that I co-supervised. If you've met me, I'm on the taller side of things, and my students were, in fact, even taller than me. So I think that was a cute photo. And this one I sort of like, and it's sort of just a little bit of a curiosity. The University of Sydney, where I am now, is our oldest university in Australia. It's 175 years old. That's maybe not that old by European standards. And also because we don't have any history of our own, we actually borrowed our logo, merging it between the University of Oxford and Cambridge, essentially. So hence we have a lot of lions on our campus. Look, so in terms of setting the scene in some way, I have this slide, and what it says is what was in Australia's flood guidance to the current update. And I'll read it. And it says, given the uncertainty in rainfall projections and the considerable regional variability, an increase in rainfall intensity or depth of 5% per degree Celsius of local warming is recommended. And I know that for this audience, you already know that that wouldn't be consistent with the current science. But, I had put in a research proposal as well as, Ashish and Rory and others, really trying to understand how extreme rainfalls are changing in Australia in recognition of the fact that, people wanted answers to how floods were changing and they didn't feel particularly confident in this guidance. So I'll present some of the research and then I'll present how the guidance worked and didn't work. So I like to start with this notion of, well, what are our lines of evidence for climate change, and in particular for how extreme rainfall might be changing with climate change. And the first one is the physical relationship, and I won't harp on about this, but obviously we have the Clausius-Clapeyron relationship, and that dictates to a large extent how extreme rainfalls might be changing. But then there's also historical trends. I mean, they play a very important role in our understanding of how climate change is impacting extremes, because it's observed data. I mean, we know that the data captures the physical processes. In some way, we can trust the data. So that's a really important line of evidence. And so that was work that my PhD student, Lalani, looked at, trying to understand how these trends occur across Australia. And of course, the other one is climate models, regional climate models. They're really great. They're projections. They are truly looking at the future. But they're limited by the capacity of the physics they represent. So nothing particularly controversial there. And she looked at the projections that we have for Australia as well. And this is a paper that is under review in weather and climate extremes. So I'll really focus highlighting Lalani's work and then talk about the guidance. So map of Australia, where do we have data or data? So at these locations, these are really good sub-daily rainfall gauges. The resolution is 6 minutes. We have continuous records for over 50 years at these locations. One thing that we like to claim is that we have a variety of climates. We don't really have snow, we don't really have mountains, but you can see we cover 4 different, say, I think they're the SREX or IPCC zones. And you can see that we cover a lot of different Köppen climate regions. It's very tropical in the north, monsoonal type rainfall, summer dominant. In the south, it starts to get more winter dominant, particularly on the southwest coast. It's a Mediterranean climate. It barely rains at all inland, and here we have quite temperate sort of climates. So one way to look at trends, obviously, is to take your time series, pick out annual maxima, and just look at either a sand slope or a Mann-Kendall test. And so that's indeed what we did here. And you can see that around Australia, pretty clearly, really strong evidence that short duration 6-minute annual maxima are increasing or have been increasing, say, over the last 50 years. However, if you apply the same statistical test to 24-hour rainfall, there's not much statistical significance at all, really. There's no trend that the bottom line is. So we're only seeing trends in annual maxima for very, very short duration rainfalls in Australia. Now, Australia is not homogeneous, but for a second, let's pretend that it is, and we can aggregate all these sites and just look at the send slope at each of for each of these different durations. So this is what this plot shows. So it's the slope per decade with a send slope, and these box plots represent those approximately 40 gauge stations. So I showed strong positive trends in 6-minute rainfalls, and here you can see that the slope is about 5% per decade. If you divide that by the average warming, let's say it's 0.2 degrees per decade, that's about a 25% increase per degree warming. So it's a lot. The bottom line is that 6-minute rainfalls are increasing by a lot more than what we would probably expect. And I would argue that there's still positive trends down to the 1 hour duration, but once we get to longer durations, there really isn't much of a signal. But annual maxima are not very rare when it comes to flood design. So how can we look at rarer events? Well, I think the 2 most common methods really are, you can split the sample on a midpoint. So split the sample here on 1995, fit GEVs, to the first half to the second half, look at the difference for the rare quantiles. Or alternatively, fit a non-stationary GeV with a covariate, in this case, very simply just a time covariate. And here we did a non-stationary model with a non-stationary location and scale parameter. So I'm going to show you results that are pretty similar to the previous slide. For a 1 in 2 annual exceedance probability, 2-year event, it's still very frequent. It's like an annual maxima. Both the methods give very similar results and similar to what I showed before. And that's probably not surprising. But we want to look at rarer events. And so if we look at the 100-year return period event, then we do start to notice that the rarer events, so we're just looking at 6-minute rainfalls here, the rarer events appear to be increasing more. Admittedly, the two methods don't exactly align, but I would argue that the medians here are higher than the ones for the 2-year. And that's quite strongly reflected across most of the durations. Of course, for the longer durations, we're not seeing a trend, even for the 100-year event. That doesn't necessarily mean that climate change isn't impacting on longer durations, and we'll get to that. But take-home message here really is that the rare events do appear to be increasing more than the more frequent events. And so what from a very scientific point of view, this is quite interesting because it has a natural implication for the shape parameter of the GeV. And so we published just a short technical note in Water Resources Research, arguing that actually with climate change, the GeV shape parameter is non-stationary. That's not to say that you should model a non-stationary shape parameter, but it's just to say there is evidence for that changing. And just to elaborate further, why this happens is if I've got these 3 curves, this is a GeV, just your base, let's say, your historical GeV with no change, and then we're factoring it up. This is the orange one here is the change where you apply a constant increase, right? Like a 30% increase for all annual maxima. But what we did with the green line was that you can factor up all your annual maxima and then fit your GeV, but increasing that percentage change for rarer events. So from 30% to say 50%. And these are the fitted GeVs if you only vary the location and scale. And so actually, if it's a constant proportional change to all your annual maxima, varying the location and scale will fit the change perfectly. And that's something that has been noted by other authors. Iliara, for example, has essentially published this before. So, I'm not claiming credit for that at all. But what we just wanted to suggest was, well, if the increase is not proportional, it's actually greater for rarer events, then actually you have to vary the shape parameter to get that kink at the rarer end. The thing is, and I'm sure you all know this, estimating a shape parameter with even long record lengths can be quite fraught. And so what I'll show you on the next slide is the uncertainty when you do this. So NS2 means we're varying location and scale, and NS3 means we're varying location, scale, and shape. And for frequent events, in this case 5-year events, if this is our stationary model and this is our non-stationary model, point is that these two models lie on top of each other. You can't see the difference, and their uncertainties are not that large, not that different. But if you go to rare events, okay, you can capture the greater increase using the greater increase for rare events using a non-stationary shape parameter. But the uncertainty explodes. I think it's okay to say. This pink is the uncertainty, and it is going outside the scales that we have on our plot. So not necessarily suggesting this is done in practice, but I think this is a really nice not statistical, but scientific curiosity that's worth mentioning. Look, so in terms of the implications from that paper, I think we can confidently say that, at least in historical data, rainfall increases are greater for short durations than longer durations. At least that's what we're observing in Australia. So convective rainfalls increase more than, say, non-convective. The more extreme the rainfall, the greater the increase in the quantile. I feel confident in that. And this gives evidence for a non-stationary GeV shade parameter. But what about those longer durations? Like we definitely should expect that longer duration rainfalls will also increase with climate change. And I think that's where climate modeling comes in. So again, we start with the same data set in terms of rainfall, but all the same sites. But in this case, we also have regional climate modeling for Australia. And at the time that we did this work, there was only one group that had done regional climate modeling for all of Australia. The grid's quite coarse if, when you think of regional climate models, about 10 kilometers. But, that's still a lot better than the resolution of GCMs. What they did, which was really, I think, novel, at least from the Australian point of view, was they used quite a large ensemble. So they had a lot of different GCMs, so different GCMs. And they also did some that were ocean coupled and some that were not ocean coupled. I mean, in terms of their downscaling, I should say. So we had quite a large ensemble to play with. So 15 different, let's just say 15 different GCMs. It's not quite, I mean, there are multiple ensembles from different GCMs, but just for simplicity, 15 different downscale ensembles. And I'm just evaluating how that regional climate model performed just at one site here. And this just happens to be Melbourne. The reason why I use Melbourne was just because it has the longest sub-daily rainfall record. The black is the observed. On the x-axis, I have the AEP, so frequent events, 2-year events, 100-year events, and all the different ensemble members. And the gray is the uncertainty. Yeah, look, I mean, it is a 10-kilometer grid, so it's it's not going to capture those short duration extremes. I think that's probably fair enough. But it's not terrible. I mean, we're underestimating our 1 hour rainfalls, but it's not too bad. And for the 24-hour rainfalls, the estimates are well within the uncertainties, even for the rare events. Look, I mean, sometimes when you're fitting annual maxima, the shape parameter will blow up a bit. So, there are some ensembles that don't look as great as others. But in general, this doesn't look too bad, and particularly for the frequent events for 24-hour rainfalls. And it looks even better when we average across all the sites. We didn't find particularly much evidence for heterogeneity with how the model performed. There's a little bit, but not too much. So if we average, we have all the models here, and if we average across all the sites across Australia, and this is the relative bias, so 0.5 does mean a 50% bias. It's quite large. But 1 hour duration, 5-year and 100-year events. Well, actually, yes, there is a large underestimation in general. 40%, let's say. It's not too bad. And these models actually work pretty well for the 100-year, and they just happen to be the ocean coupled models. So it's just interesting to see. But the 24-hour rainfalls are actually maybe slightly negative bias for the 5-year, slightly a higher bias for the 100-year, but really not too bad. So it's a really encouraging, I guess, result from the regional climate modeling. And this is across the continent of Australia. So if we say we trust our regional climate model, we can look at some projections. And this is what the projections look like. Now, admittedly, even though it's largely the biases are the same across the country, there is a little bit of maybe a dry bias in the north, so the projections might be a little bit a little bit less, I guess. But if we're looking for SSP3 7.0 by the end of the century, you can see, well, look, in general, 5-year events, 10-year events, they're projected to increase. unsurprisingly, the rarer the event, the darker the color, the greater the projection. And again, I'm going to aggregate these across Australia and plot those box plots with duration to sort of give us some idea of what this looks like. And I think this is a bit more telling, where the downscaling, the regional climate modeling really does show very well that rare events in purple compared to the blue, the frequent events, the rare events definitely increase more than the frequent events, and they're or at least are projected to do so. And that's really consistent with our historical observations. The other thing is that there isn't that decline that you saw. The short duration of events are projected to increase roughly the same amount as the longer duration events. There isn't that decline with duration in terms of the projections. But now we have really nice, strong evidence. Our 100-year, 24-hour rainfalls are actually increasing. And I would hazard a guess that we just have too much noise in our historical observations to really pick up probably these increases that are projected. I really like the next plot because it's just talking about the AEP change. It's just talking about the frequency change. So here is the change in the top panel is the change in the y-axis. Here is the change in the x-axis. And really, if we're looking for a ballpark figure in Australia, let's say for 24-hour rainfalls, we can just say, look, the 100-year rainfall is going to become the 50-year rainfall by the end of the century. It's a factor of 2 change. And I think that's a really nice, what we say, back of the envelope, I guess, calculation, and a nice sort of sanity check if we're ever doing any projections in Australia. The last one, well, not quite the last plot that I'll show on this, but the second last one is the dividing the changes by the temperature change projected in the GCMs over that time horizon. And that's where you can see actually these short duration rainfall changes are really less than what we were talking about in the observed record. We're seeing some maybe superclassius clapeyron scaling, but not a huge amount. And really these 24-hour rainfalls are probably increasing or projected to increase around the classius clapeyron rate, but only for the 100-year. For the 5-year events, the increases that are projected are much less. So having said that, we also did compare using our observed data and fitting a non-stationary GEV and then projecting it out with the temperature increases that are projected by the GCMs. And it's not really a surprise that this is going to look like our observed record, but it's just nice to, I guess, compare. So here we have the quantile change using a non-stationary GEV that's being projected out just on a temperature covariate. And you can see quite quickly, because on the next plot, I'll show you again the quantile changes that are straight from the regional climate model. The observed changes are so much larger for short duration rainfalls. They're just, 5-year, 100-year events, 50% change projected by the end of the century versus something about half of that. But then on the other hand, for the 24-hour rainfalls, because we don't see an observed trend, even when we project it out, we don't see an increase. And you can see the much, much larger uncertainties that are present in our observed record. So in sum, I can say there is a negative bias in our regional climate models for extreme rainfalls. That's okay. I mean, we can expect those to improve with greater resolution. The projected increases for short duration rainfalls are less than the observed changes, but the projected increases for long duration rainfall are greater, right, than what we see in the observed record, and indeed with less uncertainty. Now, I just want to take a slight aside because since that time, there was some work published by a team out of Queensland in Australia, and they actually looked at all the regional climate models from all the groups across Australia. But just noting this is daily. They're looking at daily rainfalls. But it's quite a really large ensemble. This is all the data we have for Australia, full stop. And so, except for maybe higher resolution local scale, in terms of anything that covers Australia, they captured it. So you can see uh, these are the four different groups for your interest. So we have a Queensland group, we have a group based at our national science organisation, the CSIRO, or they're called ACS. We have BARPA, that's actually our Bureau of Meteorology. It's very hard to get your head around all these things unless you're like in the know, I guess, because the ACS is an organisation that sits above those two. Um, and NARCLIM is actually based out of the New South Wales government, New South Wales state government, but also working with Jason Evans from the University of New South Wales. So Queensland government, Australia, CSIRO, our Bureau of Meteorology, and let's say New South Wales government. So they have done all sorts of different, they use different models, different ensemble members. You can see they use different they actually all use different regional climate models as well. I mean, these two both use CCAM, but Bureau uses BARPA, NARCLIM, New South Wales uses WRF. Anyway, so lots of different models are going on, but they did an absolutely amazing job of comparing all these results. So this is CMIP 6. The projections are for the end of the century, so similar to what I showed you before but they've standardized it on the temperature change this is RCP 7.0, but yeah, standardized on the temperature change. So 10-year, 50-year, 100-year, the CMIP 6, and then we have the four downscaled groups. So Queensland, CCAM, BARPA, NARCLIM. So you can see that, look, there's a lot of information here. One thing to convey is that the different groups have very different ensemble results. So if we just focus on the 100-year event, Queensland group projects 4.5% per degree warming across Australia. CSIRO projects 7.7%, then we have 10% by the Bureau of Meteorology, and then less 6% by NARCLIM. So they're actually fairly different. They're all projecting greater increases for rare events, which is what these box plots show. But yeah, look across Australia, very different results from the different models. Yeah, this one, I just, again, a nuance, but this is the change in the GEV parameters from the historical to the future. And you can see indeed, the models are saying the same thing that we saw in the observations. In general, there is an increase in the location scale, but also a projected increase in the shape parameter from all the groups. The shape parameter, of course, has quite a small range, so it's a relatively small value. But yeah, just for your interest, we have projections for all of Australia, but they do have some divergence between the actual results between the groups. Look, so given all that science, we're coming back to the fact, well, our guidance says we should increase our extreme rainfalls by 5% per degree local warming. And clearly that's not quite consistent with the science. So look, it was a perfect storm. We happened to be doing this research, and the federal government decided, someone got funding in the federal government to actually update the guidance. And so that was our role, or my role as the lead author, to try and, they had a project plan, and I was my role was to instigate it. So the first part was to write a discussion paper stipulating the principles of how the update would happen. Then there was a peer review of the science. Then we published some draft guidance, which went to stakeholder consultation, which was brutal but good experience, I guess. And then the guidance was published. And currently there's workshops underway trying to understand, well, is the guidance working as intended. Everything is public. So if you're interested in the discussion paper or the draft guidance, they're at these links, and the final guidance is in another link, which I hope I included as well. So everything was made public for transparency and to try and build, I guess, confidence in the process. So I'll have one slide on each of these steps essentially, or just a handful of slides, and hopefully then leave time for questions. I'm covering the discussion paper in one quote, and I quite like this quote because I put it up in some industry forums, and people take photos of it. They quite like it. I think it's quite a strong quote. We said in our discussion paper that decision makers often have a legal and/or other duty of care to their stakeholders to consider climate change. But there is little information on how to consider climate change in design flood estimation. As a result, practitioners feel hamstrung by the guidance that is currently provided, and decision makers are concerned that the latest science is not always being applied appropriately in policy outcomes. I do know that some people who were decision makers felt a little bit uncomfortable with this, but overall, the people who did the survey or the stakeholder feedback on our discussion paper and were asked to comment on this quote, 3/4 agreed with this quote. The reality is that this was the prevailing feeling among decision makers and consultants, and hence there was a strong impetus for updating the guidance. So the second step was to do a systematic review. The thing is, we didn't have funding to do new research. So our job was essentially to review all the science, like I've just presented to you, the science that I've presented to you like that, and say, well, what can we say from this science? We did a systematic review to try and make things reproducible. Not so much even reproducible. I mean, that reproducibility is, of course, very important, but the reproducibility builds defensibility. And that was what we were trying to achieve. It was a lot of work to do an extensive literature review, and all the co-authors here had their own sections to review, and Acacia and Timothy, who Acacia's at the Bureau of Meteorology and Tim is at the University of New South Wales, did a lot of the calculations. So we're very fortunate to have them help with this work. And the calculations essentially were a meta-analysis where we did the same thing that I've just shown you, trying to bring everything down to a scaling per degree of global warming. We can have an entire discussion of whether that's just how justifiable that is. But in the end, there's a pragmatic decision to be made on how can we standardize all the information that we have. And this was a decision that we felt was practical, but also scientifically defensible. Indeed, global temperatures do drive atmospheric processes and the warming that causes the atmosphere to hold more moisture. All the calculations are on GitHub. Everything is transparent. So these are the results. I'll take you through them one step at a time. We split our data set, or all the papers that we found that had projections or historical trends into whether they were less than 6 hours or greater than 12 hours. And the categories of lines of evidence or information were observations, historical trends, regional climate models, general circulation models, global climate models, and scaling, which is just precipitation temperature associations. And so this is one result, right? So this is for 24-hour rainfall. There's one paper in Australia that looks at changes in PMPs. They use two different scenarios. So two different temperature trajectories that we can divide by, hence the two diamonds. And these bars just indicate the variability across Australia because the projections were on a grid by grid basis for Australia. So that's one line of evidence. More lines of evidence. We have regional climate modelling, so projecting slightly higher increases than our PMP estimates using general circulation models. Here we have another study. You can see I'm pretty confident this dot is the work that I showed you from my student. So, she didn't show changes in 24-hour rainfalls really. So the median is less than 1, but there was a very large variability in our results. So hence this very wide uncertainty bar, I guess. Here's an example of a study that only looked at 1 or 2 sites across Australia. So we're probably, given the amount of variability in observed records, we're probably not going to put much emphasis on that study. So it's grayed out. This is what the data looks like. So if you try and make an inference on how climate change is going to impact long duration rainfalls in Australia, this is what you have to work with. Like if you look up the published literature, this is it. There's a lot of uncertainty and a lot of scatter in the science that is done. And I think that's okay. I mean, we feel comfortable with uncertainty, but for decision makers, that's obviously tricky to deal with. And for less than 6 hours, and if we're honest, it's mainly hourly data that's there, we're very much relying on observed records to inform how the future is going to change. We're being led by observed studies because that's the only lines of evidence we really have. So, and I think you can see that, well, even though I mentioned that extreme rainfalls, the rarer the event, the greater the increase, this sort of trend, there is a lot of uncertainty. So we weren't able to quantify that, but we were able to say something about long duration versus short duration. So some of the authors went away and summarized all this data, and this is a big table, which is in the supplementary. But we all did our own independent analysis. We weighted all the information as best that we could. And these are the 1 hour and 24-hour ranges, likely estimates or scaling estimates that we came up with. Then we had a meeting and we debated what we would come up with. And then finally, I'll show you in 2 slides, we came to consensus for a number. So this is the climate change considerations guidance. And this is the table that's in there. So this is the link if you're interested. If you're really interested in the guidance, I'll send me an email and I'll point you to it exactly because the website's not so easy to navigate. But this is what we've said. For 24-hour rainfalls, we're going to say that you factor your rainfalls by 8% per degree of global warming. And for 1 hour rainfalls, 15% per degree global warming. Now, there's a few things here. One is the 8%, you might be like, oh, that's more than 7, which we usually quote for Colossus Clapron. Admittedly, Australia is warming a little bit faster than the Earth overall, and actually, if you divide by Australia's temperature change, this does come out to be about 7%. But it's a very convenient way to standardize on global temperature change. And so, and between these, you can interpolate. The other thing to note is that we deliberately biased our evidence or our intuition to 100-year events. We know that most people in Australia will use this for flood studies. In Australia, the 100-year event is the default flood planning level. So we're really trying to bias our information to those rarer events. Look, the other thing is just to note what else changed. Okay, so we changed the scaling factors, as I showed you. No longer 5%, 8% and 15%. The other thing is that we actually said that you can't just use the historical IFDs if you want to plan for, let's say, a temporary structure that needs to be designed now. You don't just apply these scaling factors for 2100, you apply them for now because there has been some warming since the intensity, frequency, duration curves were derived, and that needs to be factored in. As I showed you, the rates of change do vary with storm duration, but one thing that we've also said is they apply up to the probable maximum precipitation. Previously, they were only applied up to the 100-year rainfall. So we've been, I think, quite strong in this to say, look, we do believe that the rarest rainfalls are also increasing. Global temperatures are used for factoring rainfalls, not local temperatures. So there's a lot of conversations that can happen around that. And we did provide guidance for other factors. I don't go into that here because there's not really enough time. We provided some guidance around how you might resample your temporal patterns for climate change if you feel there's any evidence for them changing, for example, becoming more front-loaded. The other thing is losses. So we do give scaling factors to say, well, the soil is getting drier in Australia. This is a very this is possibly a little bit more specific to Australia, but in Australia, very much our soils are getting drier, and so we came up with factors to factor those losses, so make the losses bigger, which means the soils are drier before the rain actually falls. Look, so how do we go? Um, it's a good question because obviously we got stakeholder feedback and I had to read it all. We did do a survey. A survey is probably not as informative as what I hoped, but it's not bad. And there was a few questions in there. Does the update provide consideration of different climate scenarios? Let's say happy is blue, not happy is red. Yeah, people are pretty happy with that. The update provides an easy apply method in practice. Nah, not so much. I mean, this sort of confused me because really it's just a percentage change. Like how hard can it be? But I'll get to that. The inclusion of worked examples helps interpret the guidance. People were really happy with worked examples. That was really nice. The update provides guidance on how to apply the uncertainty. Fairly neutral, I'd say. The updated guidance reflects the current science. I think we got a big tick for that. And that's really nice and that's really comforting. And is the update applicable across design flood approaches? Generally, people are pretty happy. But they weren't happy with easy to apply in practice. And I have a lot of sympathy for that because you still have to pick a temperature projection. And how do you do that when this is what the temperature projections look like? And we can't expect a practitioner to be an expert in climate science. Indeed, by definition, each of these SSPs is equally likely. So it's not easy to do. So this is our IFD baseline. By 2050, maybe not so much divergence, but by 2100, if we really mitigate our carbon emissions and if we go for broke, there is a 2-degree temperature difference. And so there is something around that practitioners are still going to struggle to decide what to apply. And there's an element of trying to decide whether they do adaptive management approaches or whether they decide to pick, higher temperatures based on their risk appetite. Those conversations, I think, are still really ongoing. However, I do want to say that the Australian government does provide an example in their risk assessment. So they did a risk assessment for Australia, and they, I think, provide some really nice pragmatic guidance. And the suggestion is that for a time horizon of 2050, you just pick global warming levels of 1.5 and 2 degrees. And I think that's really nice because that's just 2 scenarios to model. And for 2090, they suggest 2 to 3 degrees. And again, that's very nice because if you've already done your modeling for 2 degrees, then that maps to a 2090 scenario. And I think that's a really nice way of bookending the possible decision making that you might have to deal with as a practicing engineer. But yeah, admittedly, how this is playing out and how people are applying it is still a conversation that is being had. I mean, people are in Australia updating their flood studies for climate change, but then the question is, well, are those differences something that we're going to adopt? The reality is that our design flood guidance changed 20 years ago, and that also changed the design flood level. So there's a lot of practical aspects to it as well. But I think I'll leave it there. And yeah, really happy to take questions. And if you don't feel there's enough time for questions now, happy to be contacted outside of this as well.
Thank you very much, Conrad. Of course, there are minutes we have, I think, up to 10 for having questions. I think the presentation is very, very interesting and is also touching a lot of, I think, interest for our working group. Yes, Sergey?
Yeah, hello. Sergey Vorogushin from GFZ in Potsdam. Thank you very much, Conrad, for this was really excellent talk, really insightful. My question is about spatial variability, or did you have an issue whether to apply these factors for the entire country. I mean, Australia is a big country, and the results from the climate models are show really distinct spatial variability. How did you go about that?
Yeah, I really appreciate that question. I'll put up yeah, let's say I hope this works. Like for context, like we can show this slide because it does show spatial variability. Yeah, look, it's a really it's a there's a longer conversation to have about this because if you're going to incorporate spatial variability, then we probably have to rely on one line of evidence, which is the regional climate model. So we have to have faith that that's probably our 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 best estimate of climate change. The reality is that these results that I'm showing you weren't available when we were doing our work. There was a lot of feedback to do with, we should incorporate spatial variability. So I want to say the simple answer is we didn't include it because we were just commissioned to do a literature review. Should we include it? I think the answer is yes. Do people want it? Yes, very strongly consultants want it. And I do know that the Bureau of Meteorology, at least in Australia, under the Australian Climate Service, is looking to try and convert these to some sort of factors. So yeah, because it doesn't quite show up in this picture, but like around this part here, around the southwest parts of Australia, these models have quite a dry bias, but otherwise there's a very strong drying trend, and so this part of Australia behaves very differently to other parts of Australia. So we couldn't do it because we just didn't have the information, I think, at the time is probably the answer. But yeah, it's definitely something that should be looked at.
Thanks. If I may pose another question. It's with regard to how this guideline is going to be applied. In Germany, we have quite a conversation with practitioners, and they are reluctant to have these climate factors because they argue, well, how do we go? We just updated our infrastructure. If a new guidelines will be put in force, we kind of need to rebuild this again, and they're afraid of that. So new investments and so on. So is there kind of embargo time for updating the infrastructure, or how do you deal with this in Australia?
Yeah, look, we have the same issue. So there was one comment which was, why are you updating the guidance now while we're having a major infrastructure update? And it's like, well, there's always infrastructure happening. I don't know. And definitely there was other government organizations which asked for more time. The reality is that the look. One thing that's apparent to me recently, that I've noticed is that there's enough like this is not a regulation, this document. It's a guidance.
Okay.
And there's a very, very specific nuance there that you don't have to follow it. Now, if you don't follow it, you have to have a very good reason for not following it because everyone treats this as the Bible of hydrology. But state government organizations and state governments and sometimes local governments are actually responsible for different types of infrastructure. They're allowed to have their own regulations and guidance as well. And so it's a bit of a murky area where just because this is the national document doesn't mean that a state government doesn't say, yeah, okay, apply, do the modeling, but you don't have to apply it. I mean, I'm not saying that's what happens, but it's just yeah, maybe a better way of phrasing it is in one jurisdiction that I know, they're like, okay, this is the latest science, we trust it, but this is a guidance, this isn't a regulation. So how are we going to update our dams? Well, chances are what they're going to say is they're going to say model these increases, but you don't necessarily have to update your dam unless the impacts are over a certain threshold. So very much this is going to come down to a case-by-case basis. But I recognize that we have created a very large headache for a lot of people in Australia. And so now it's onto sort of each individual authority to respond. I recognize it's a really long-winded answer to say, like, we're struggling with the exact same thing. But there are ways around it, which is to essentially have for decision makers to put in place rules like model it, look at what the impacts are, but you don't have to change your infrastructure necessarily. Like, are we okay with with just accepting a little bit more risk? That's all. Yeah.
Okay. Thank you. Interesting.
Any other question?
I have a question.
Yes.
Can you hear me? I am Aldo Fiori, Roma Tre University, Italy. But first of all, congratulations for putting together a few simple numbers out of such quite large uncertainty, because this wasn't totally unexpected. So I think it's very great what you did. Just one thing that escaped me. So this very simple increase of percentage increase are for all the durations, or also from 1 hour to 1 day, or I think you said that, but it escaped me somehow, because I guess
Yeah.
Sorry.
No, I was getting to the end and started to go a bit quickly. No, so we said for 24 hours we said 8%, and then for 1 hour we said 15%, and then we provided like a lookup table, and to be honest, we had to provide something, and I think it's okay to say there isn't much information. So what we applied was exponential decay. So it's very much biased. The 1 hour sort of rainfall change is very much biased towards 1 hour, 6 minute. And then you're by the time you get to about 6 hours, it's pretty close to that 8%.
I see. Okay, well, many times people say, I mean, they use the Clapeyron limit, and which is clearly, I mean, not a good argument. And I mean, this percentage shows that, I mean, that percentage of Clapeyron is clearly underestimation. I'm just curious about this 8%, because I mean, the data that you show, the 50 years data, that do not show, I mean, a clear increase. So I think you discussed that, but probably that also part of the discussion that I missed, because even so 24 hours, because also, I mean, here in Italy, we have a very long series of data. We have 200 years of rainfall registration, and we didn't see, I mean, a significant trend at all. I mean, the daily, and just like in Australia. So I wonder how you explain, I mean, to stakeholders, I mean, this 8% increase.
Yeah, it's hard because if someone wants to, they can take their rain gauge, look at the 24-hour rainfalls and your maximum, look for a trend and say, well, we didn't see a trend. And that does happen. Yeah, so like thankfully in general, because we had the 5% before, and to Sergey's question, there was state government guidance which was suggesting 7%. Look, the 8% has sort of everyone sort of accepted that. Like they said, look, it's about Clausius Clapeyron, and there's been a general acceptance of that. Despite the fact that you don't see it in the historical records. And really, from a scientific point of view, that 8% really is based much more on the climate modeling.
Yeah. So would you see that this is sort of a cautionary, sort of estimate, just to be to stay on the safe side, so to speak?
No, I mean we still feel, or our feeling is that it's a midline. Like so this, I'm sorry, I'm just going to draw. So this is the uncertainty that we put around it. So
Yeah.
2 to 15%. So we do believe that it's like the mid-range scenario, and I guess we're suggesting or arguing that, well, there's just too much noise and variability in our historical records still that we just haven't seen those increases. But having said that, I mean, there's the papers published by Sun et al. And Westra et al., which do show that on average, globally, 24-hour rainfalls have increased by around the Celsius per mark. And I think I mean, one of the battles for us is to say, look, like, I know you want to rely on your local data, but the more local you get, the more noise you have in your data, and the less likely you are to see a signal. And hence, we're trying to really push this with this guidance work to try and push people to consultants or practitioners to really consider you know, okay, we might have a lot of noise in our data, so let's look at globally what we might expect. So that's yeah, that's part of, I guess, the conversation that we've been trying to have. And in that discussion paper, that's something that we wrote, that you should look at more evidence than just your one particular location of interest.
I see. I see. If I
It
may,
doesn't mean that people
sorry.
believe us, but yeah. No, I was just
Sure,
gonna say, doesn't
sure.
mean
That's a different matter. Yeah. But just a very last point, if I may, I mean, so the recipe, it's if I understand, is very simple. So I take this table, there is an interpolation zone. So okay, and now the point here now is to choose the right projection for the temperature, right? And here you have a different choice. So again, what is your recommendation to have two choices, or to produce both prediction for floods, for discharge, or I missed that part, sorry.
No, that's fine. Look, my recommendation, but it follows the Australian government essentially recommendation, was if you pick a horizon, which is, let's say, 2100, in this
Yeah.
case, oh, my apologies, then you would pick, sorry, you would pick 2 degrees and 3 degrees. Like, pick maybe something that you think is quite likely, and then something that is a higher end sort of scenario. So just trying to book.
That's fine, but at the end, I mean, what do you pick? You provide both, and then I mean, the designer has to pick something. Or I mean, the designer, you cannot use. I mean, maybe you can use one and verify with the other, or the other way around. But it's what is the recommendation?
Yeah. So, I mean, officially there isn't one. I mean, my recommendation would be to just do a cost benefit analysis. And if the extra investment is, so let's say for 3-degree warming, is just disproportionately large, then you just try and put in some adaptive management technique. You just try and allow for your infrastructure in some way to change. But that essentially it's to do a cost benefit analysis. It's actually the dollar terms.
Okay.
I'm afraid that if someone was to do that, then probably nothing will ever happen. But yeah, it's
Yeah, sounds
yeah.
reasonable, definitely.
No easy answers.
No, of course, there should be an easy recipe, especially for this when uncertainty is so large. You have to use a pinch of salt. I mean, in every decision. And yeah, thank you very much.
Other questions from audience? In case I have just Dirceu, maybe?
Just a short question. I was
Yes.
wondering if there are any studies that use the CPM, convective permitting models, and if there is, would they be more reliable to estimate this change regarding temperature change?
Yeah, no, it's a really lovely question, because yeah, that I don't, to the best of my knowledge, because I try and go to the climate science conferences in Australia as much as I can. It hasn't been nothing has been published yet, but the work is happening. So It has. Sorry, so let me rephrase that. These guys, Narclim, they did use a smaller area, so about this big, and then they did actually do convective permitting modeling on that. But I don't think the results are published. I think like the data has been published. So there is some convective permitting modeling, and now under the Cordex program, all the groups have coordinated to model just our main cities. So to try and see and evaluate against radar estimates. So that work is happening. But yeah, I think it's okay to say without offending this group who have done a lot of work doing regional climate, like convective permitting, it's very much in its infancy. So this group at the last conference I went to showed us some convective permitting modeling for Australia. They just did like one scenario for a short horizon, and they did it across all of Australia. Amazing work. And then they just found very large biases in the tropics because they have some parameter that isn't quite right. So it's happening. It's just it's not quite there yet, and not quite published. Or at least that's to the best of my understanding. But yeah, it'll be really interesting to compare. Yeah.
Okay, thank you.
Thank you, Conrad. And I have a couple of comments. There are a lot of information and everything interesting. I found very interesting for us as scientists the methodology of the sort of meta-analysis that you carried in the review paper. So putting together different study observation, climate model, RCM, GCM, and with independent evaluation and trying to compare them. So I found that very interesting because we have different source of information, different evidence, a lot of uncertainty. And secondly, and I think it's very interesting also for this group because we are dealing with hydrologic design and communication, I found very interesting the process, the involvement of stakeholders at the first stage, so at the very beginning of the study, so consultation with the stakeholders, and then in the middle, and then the feedback at the end. So do you think that this kind of involvement was useful for developing this study?
Yeah, I think there was I think two keys to, let's say, success. One was that there was like bottom up met top down. So we're publishing a lot of science, but then we had the authority from a federal government agency who commissioned the study. So as soon as that happened, that top down, then you can't not listen to a government agency. So I think that's when the stakeholders really started to listen. Really, when the study was commissioned by Department of Climate Change, Energy, Environment, and Water, so they're a federal agency, and yeah, I think it was presented at conferences, it was presented at workshops online all through the process, and I think people started to feel like, okay, this is happening. Like we have to get on board. How, as opposed to, because I think there is always going to be that not resentment, but that pushback of like, well, I mean, flood risk always changes. You get new data points, it's going to change again. So there's always going to be a bit of pushback. But I think when people realize that there was those workshops in the beginning, then that just created this momentum that this is happening. So there was a resignation to the process, and then how can we do it in the best way possible? So I think that early stakeholder feedback and discussion paper was really good, even if not all the tenets were necessarily adhered to, just prepping people for the fact that this was going to happen. I think was a really sort of good an important part of the process.
Thank you. I think that if there are no more questions, it's more 10 past 10 in Italy and several different hours everywhere. So I think that I could really thank Conrad for his availability for this first webinar. And it was much, much interesting, I think, and I hope for all of you. And thank you to people attending at any time. And I don't know, Svenja, if you want to say something about future webinars. So thank you very much, Conrad.
Yeah.
Thanks, Elena.
Yeah, so also from my side, many thanks for that super interesting talk, which was so relevant also for our group. I mean, with all these stakeholder inclusions, that's exactly what we are also aiming for. So very, very good example on how to do that. And for those of you who are attending this meeting but are not part of our working group, feel free to sign up. So just go to the IAH webpage. And you can sign up for our working group there, or just reach out to Eleonora or myself if you want to, and we can give you more information. And this will be, or this is the first part of our new webinar series. So we will continue to organize this in future with different topics covering all the hydrological design parts there are, and there are many. So we hope to see you also in future webinars. We will keep you updated, of course. And many thanks to Eleonora and also Yu-Yong Kim and Avinesh for organizing this very nice webinar, because they are the leaders of the SubFlap group. And they really did an amazing job for giving a perfectly fitting first webinar talk here. Thanks.
Thank you to all. Bye.
Thank you very much. Thank you. Bye-bye.